Hi, this is Suresh. I would like to walk you through my analysis of the data generated by a wearable device called Spire. Spire tracks the user's respiratory rate and uses it as a surrogate indicator for the wearer's state of mind. Average humans breathe more than 8 million times a year, but most do a poor job. Slow, deep breaths promote a state of calm, while shallow, rapid breaths promote stress. Spire provides real-time feedback through the mobile app tethered to it to improve one's breathing pattern. Managing breath is part of traditional sciences like yoga, but modern science ignored the benefits. But that is changing now. Concept of a wearable for tracking respiration is a recent one. The motivation for this project was to leverage my own data to draw parallels with current theories and explore new correlations. Current research and visualizations in this area mostly focus on comparing the reliability of the new devices vis-à-vis established ones, as well as some high-level visualization of the benefits. As you can see here, the visuals indicate high reliability and clear benefits of using devices like Spire. Also, current research focus more on the science behind the benefits and less on the analysis of user data in the wild to draw insights. In contrast, my goal here is to leverage usage data to create insights. My objectives are understand the important impact of temporal factors like day, time, seasons, contextual factors like work, to look at the impact of daylight saving changes, and lastly, understand correlations between activity levels and states of mind. The expected results are higher stress during work hours, lower stress during weekends, lower respiration rate during sleep, increased respiration rate in summer, negative impact during daylight transition, improved benefits through sustained usage, and increase in activity levels leading to lower stress. To arrive at the design for the visualization, primary objectives like comparison, relationship identification, distribution and composition analysis were considered first, followed by the range of time and categories involved, as well as the number of variables and data points. Accordingly, a variety of visuals like bar chart, histograms, pivot tables, line charts, etc. were chosen. In the following slides, we will look at the objectives, the visualization methods, the visuals, and the interpretation and insights of the results. First off, we will look at the distribution of the raw respiration rate data. Histogram was chosen as the appropriate visualization method and plotted using matplot, and the corresponding normal distribution plotted using CBOM. The distribution looks near normal with a mean of approximately 15 breaths per minute. Both the plots show a slight skew to the left around the mean, which could imply a higher density of data points to the left of the mean. Next, let's look at the variations between breath rates of workdays versus weekends. The left skew of the workday data is not visible in the weekend data, perhaps due to the smaller weekend data count. To compare the sizes, a pie chart was drawn. To validate, a bar chart using the streak data created by the device was drawn. Although the box plot does not indicate any difference in the medians, the mean of the workday breath rate at 15.31 is higher than that of the weekend. It shows up in the higher activity level of the workday too. Next, the variations between day and night was looked at. As earlier, overlaid histograms of the distributions and a box plot were created using the raw respiration data and a bar chart plotted using the device data. The histograms clearly show a right shift of the mean at night, and the box plot shows a corresponding shift in the median too. The higher breath rate of 15.6 at night compared to the 15.0 of the day was counterintuitive initially. However, on further reading, it was learned that the respiration rate of healthy humans is more shallow and rapid during the night. This also explains the counterintuitive duration of streaks observed in the last slide. The next objective was to compare respiration rates between work hours defined as between 9 a.m. and 5 p.m. on weekdays, and the rest of the time, other than sleep hours, defined as personal time. Histograms and box plots were created. This was also counterintuitive. The mean of respiration rate is clearly shifting right during personal time. There is a corresponding shift in the median too, as seen in the box plot. This needed further probing. A drill down done at an hourly basis showed two peaks and a valley, both in the raw and device data. The first peak at 2 a.m. matched the earlier observation of higher rate at night and dropped till 3 p.m. and then moved up again till around 9 p.m. A pivot table created between day, time of day, and the respiration rate also showed a corresponding pattern, with a peak of respiration rate at around 2 a.m., dropping from there and rising again around 3 p.m. The higher focus during work hour was also sounding logical. Next, box plots were created to look at the calm, tense, and normal states of mind based on the raw respiratory rate data. The spread is quite distinct. Mean values were found as calm 8, normal 15, and tense 22 breaths per minute. Drilling down, a few more interesting trends were seen. A typical workday produces a lot of short focus streaks. In contrast, activity streaks were few but longer in duration when it happens, indicative of those walk and workout sessions. Next, we will look at the seasonal variations in breathing. Line histograms were used to compare the distributions and a box plot created to compare the spread. Both showed similar trends. Breath rates show a distinct shift to the right during summer. Summer plot is also flatter at the top, indicating consistent elevated rates. Box plot is also consistent with the expectation of elevated breath rates at higher temperatures. Multiple studies talk about higher rates of accidents and heart attacks during daylight saving transition. We will now look at corresponding changes in the breath rate. Box plot and line histograms were drawn. Both showed clear uptick in breath rates. Let's look at some time series plots now. Day-wise line plot was expectedly cluttered given the number of data points. The box plots and line plot of the monthly averages show indications of a slight drop in breath rate with time, indicating the benefits of using a device like Spire. Looking for more indications of the benefits of using the device, a pivot table of year versus day and line plot using the raw data were created. Also, bar charts using the device generated data was drawn. Distinct favorable movement in numbers of activity, focus, and calm streaks were noticed. Corresponding evidence of movement in the right direction in the total duration of streak minutes per day for calm and focus streaks can be seen. Understand time-related trends. Few more time series across months, days of the week, dates of the month, and the seasons were plotted. Given the number of data points, line plots were chosen. The bump up in calm and sedentary durations towards the end of the year could be the holidays effect. Slight bump up around Wednesdays can be seen. No major trends were seen in the plots across any particular month. Next, a lag scatter plot to look at the movement of the breath per minute measurements across time and an autocorrelation plot to look at cyclical trends were created. The first one indicate weak but positive relationship and the second shows no cycles. Lastly, a bunch of scatter plots were created to look at correlations, if any, between the categories of mind states using the streaks data. The scatter plots does not seem to indicate any dependency or correlation between states. As to the future direction, study of a broader user base over a longer time frame would be great. Learning more about the data of an individual user over time should help add personalized configurability to the product settings. I will now wrap up with the main conclusions. Respiration rates have a near normal distribution. Workday breath rates are slightly higher than weekends. Breath rates at night was found higher than daytime. Workdays have short but frequent bursts of focus. Also, the breath rate of summer is higher. A small but distinct shift in breath rates was observed during the 3 days following the shift to daylight saving. The improved durations of positive streaks seem to support the long-term benefits of using biofeedback devices like Spire. Thanks for watching.